Problem 1. Compute the electrical conductivity of a cylindrical silicon specimen 5.1 mm in diameter and 51 mm in length, in which a current of 0.1 ampere passes in an axial direction. A voltage of 12.5 volt is measured across two probes that are separated by 38 mm. And part B, compute the resistance over the entire 51 mm of the specimen. So in this case, in the first part, we have to find the electrical conductivity. So electrical conductivity is represented by this symbol sigma, which is the inverse of resistivity, which is represented by rho. And resistivity is equal to the resistance multiplied by the cross-sectional area divided by the length. And on the other hand, the resistance can be found by the dividing the voltage with the current. So in this case, let's find first the resistance. So resistance will be equal to V over I. So V is the voltage, 12.5. I is the current, 0.1 ampere. So if you divide 12.5 with 0.1, so you will get 125. So 125 ohm. So this is the unit of resistance. So using this value of the resistance, we can find the resistivity. So resistivity represented by rho is equal to the resistance 125 times the cross-sectional area. So cross-sectional area is due to the diameter, okay, because it is circular. So area of the diameter is equal to the pi times diameter square. Diameter is 5.1 millimeter. 5.1 millimeter is actually 0.0051 meter, okay, square, divided by 4. And then over here is the length. So we have the length of 51 millimeter, but this is the length of the whole specimen. The resistance is being measured, that means the voltage difference is being measured in a length of 38 millimeter. Okay, so we should take this value because this resistance value was corresponding to this voltage difference, and then this voltage difference is for this much length. So you cannot take 51 millimeter over here, you should take 38 millimeter. So 38 millimeter is actually 0.038 meter. So if you will calculate it, then you will get a value. So the resistivity value will be 0.067198 ohm meter. So resistivity units are ohm meter. So therefore the conductivity sigma will be equal to 1 over 0.067 198. Which is equal to 14. And its units are of course inverse of So this is the conductivity. So in part B, compute the resistance over the entire 51 millimeter length. So we need to find the resistance over the entire 51 millimeter length. So this we can find by using this equation. So you can rewrite this equation in terms of this. So rho is the resistivity. The resistivity is actually now a material property. So this will be a constant. So it will be 0.067198 multiplied by length. So length is the entire 51 millimeters. So which means it is 0.051 meter divided by the area. So area is the same, pi divided by 4 into 0.0051 square. So we can calculate it. So we get 167.76. Oh, so the resistance of the units of the resistance are ohm. In this case, you can see that 125 ohm was the resistance for 38 millimeter length, but as the length was increased, the resistance was also increased. Problem 2. Using the data in this table, compute the resistance of a copper wire 3 millimeter in diameter and 2 meter in length, and then there is part B. So first let's find the resistance. So for the resistance we can either use this equation or this equation. This equation is for the resistivity, and area of the cross section is known, and length is also known, which is 2 meter. And resistivity we can determine from this electrical conductivity values. So in this case I will apply this equation. So it is a copper wire. The conductivity is 6 into 10 to the power 7. So if I apply this equation, so I will write it like this, because this is the resistivity. Resistivity is reciprocal of the conductivity, so it will be 1 over 6 times 10 to the power 7 equal to resistance. This we need to find. Area of the cross section is 3 millimeter wire, so pi divided by 4 into 3 millimeter, which means 0.003 meter square, and divided by length. Length is 2 meter. So I will calculate it for the value of R. So in this case I will get a value which will be equal to 0.0047. Resistance, so it will be ohm. And in part B we have to find the current flow if the potential drop across the ends of the wire is 0.05 volt. So I can apply this equation. So let me write it over here. 0.05 volt is equal to current times the resistance, so it will be 0.00472. So in this case the current I can find is will be 10.6 ampere. So in part C, what is the current density? Okay, so part C, what is the current density? Current density is actually nothing but the current per unit area. So current density is represented by J. It is the current divided by the unit area. So current was 10.6 ampere. Area is pi by 4 and 0.003 square. So if I will calculate it, then I will get the answer. So this will give me this value 15 or 1.5 into 10 to the power 6 amperes per square meter. On the other hand, the part D is what is the magnitude of the electric field across the ends of the wire. So magnitude of the electric field across the ends of the wire is the voltage per meter length. So actually in this value can be found, it's like epsilon is equal to voltage is 0.05 divided by length of the wire, 2 meter. So if it is 0.05 divided by 2, it will be 0.025 volt per meter, or in other words, it will be 2.5 into 10 to the power minus 2 volt